So other type of current amplitude modification that we're looking at here, you have looking at the stimulation patterns, constant versus surge. So if you remember about that rise and decay time, that's something here where you're modifying that. So obviously a constant stimulation pattern is that the stimulation is the same the entire time. So it's just on, the amplitude never changes. With the amplitude modification here is that you can put a surge modifier on where you have a ramp up and a ramp down time. So for instance, with the Russian stim, as we showed, we had a ramp time that you can set. So you gradually increase from 0 up to that maximum over a set period of time. So for instance, if you pick a 2-second ramp time, that means it takes 2 seconds from the time that the current turns on to get up to the peak amplitude, and then a 2-second downtime. So it's more of a gradual buildup, which we said for things like Russian current makes it a little more comfortable for the patient. So in that instance where you have an on-off time, instead of when it turns on it just going right up to the intensity, now you have a buildup. Okay, so again, the rise and decay time, the rise is it going up, and then the decay is coming down, and that's something you would set with your ramp time on your unit. Okay, so looking at the shape of the electrical current, and we're going to be talking about some waveforms throughout this as they appear clinically. So iontophoresis, again, that's a unique type of stim that actually applies a medication through the body. You could highlight this in your notes. This is the only current that is pure direct current. Okay? So really important to note. So again, direct current. To be direct current, you have the flow in one direction, so either a positive or negative, and it's on the entire time. There is no interruptions in it. So this would be the only example of a direct current would be your iontophoresis. So basically what this means is you have the current just flowing in one direction, uninterrupted, and that's the only example where you would have direct current. Okay, here we're just going to be looking at some shape characteristics. So if you look at the picture up top, that is actually an example of a modulating alternating current. Now, even though you do not have a positive and a negative, you only have a positive, what we're looking at here, it can't be DC, it can't be direct current, because it's not continuously flowing. So when you see something like this, that would get classified as monophasic. Okay, so it's monophasic, it's not direct, meaning it only has one phase. You can't say that that's a direct current because it's pulsed. Okay, you can't have a pulsed direct current because that doesn't work. A direct current has to have a continuous flow of electrons. On the bottom is something that we've already kind of shown. It's a sinusoidal shape. So again, remember, you have to be able to characterize things based off of shape. And it's an alternating current. Now that's a pure AC waveform. We don't use any pure AC waveforms. We use things modulated off of the alternating current. So you'll see with some of the things that we utilize, they do utilize an alternating current, but it takes it and modulates it. You don't have a pure alternating current getting utilized. Okay, on here up top, we're showing a faradic current, so that's an asymmetrical current. So if you look at the characteristics of this, again, I'm going to want you to be able to explain these shapes. So if we look at the top, okay, the faradic current, we say that's asymmetrical. So if you look at the amplitude and the duration characteristics, so we would say the positive one has a very high amplitude, but a very short phase duration, whereas the negative charge has a low amplitude but a longer phase duration. Okay, so if you look at the characteristics of the shape of that current, that's how you would describe each end of the faradic current. On the bottom, we have what we would call a basic biphasic. This is actually what your pure tens looks like. So we have a biphasic current, we have two phases, and it's pulsed because you don't have a continuous waveform there. Okay, and again, as I said, when we talk about pure tens, or what I also call many times a basic biphasic, that's what that waveform actually looks like. So some other waveforms we have here up top, the twin pulse. So the twin pulse is what's common in what we call high volt. Okay, so if you look at the unit, one of the options you have for a waveform is high volt, and that's what high volt looks like. Now again, it's monophasic, so it's a pulsed current. Okay, so again, we don't call that DC. DC is only when the current's flowing in one direction. So it is a monophasic pulsed, and we'll talk about high volt. You can there's some other proposed ways you can use high volt just beyond the basic sensory and neuromuscular stim, and we'll talk about that when we get to it. On the bottom, we have a interferential current. So interferential is kind of a unique current because it uses two channels. So as I showed you, you cross the channels with the interferential, and it basically creates like a constructive interference. Now it uses a sinusoidal current to create it, and then it creates this effect where you get in between the electrodes an electrical charge that impacts that treatment area. So the IFC is a symmetrical, takes a symmetrical sinusoidal alternating current and basically uses two of them to create the effect for your interferential current. And then here we have what's representative of the Russian current. So looking at this picture, again, so now think about how we would describe this, okay? And again, we're getting some practice with this here. So the Russian current would be a polyphasic, so there's many phases bunched together in a pulse train. It's a polyphasic symmetrical burst, because now we're getting these pulse trains put together into a burst setup to create your Russian stim. Okay, so it's polyphasic, many phases together, put together in a burst train, and it is symmetrical. Okay, on each side of the positive and negative line, you're getting equal current on each side of that. Now, in looking at tissues and electrical current, if you're looking to get some type of chemical change, so this is a situation where the positive and negative leads you need to have in specific places in order for this to work. So in particular, when you're looking at ion transfer, okay, you're looking at, you have positive and negative ions that you'll utilize, and therefore you have to use your positive and negative poles in the appropriate placement in order to do this, okay? Now, in order for this to happen, you need to have a certain type of current. You need a direct current because you need something that's continuously applying a charge in one direction in order to create an ion change at your active lead. Okay? Again, the best application example of this is ionophoresis. So if you look at the picture, very common to most ionophoresis units, you have an active electrode which, based upon the medications all have specific charges to them. For instance, a very common medication used in ionophoresis is something called dexamethasone. Dexamethasone has a negative charge, okay? So in order to push that negative charge or get that medication to go through the skin, you need the negatively charged pole, okay, or terminal to be on that, because what that's going to do is you put the medication on the pad. When you apply the negative charge to that pad, it's going to, remember, like repels like, that's going to push the ion through the skin, okay, theoretically, and get it to the treatment area. The other electrode is going to be used as what's called a dispersive pad, okay, so you still need both to complete the charge. Otherwise, you're not going to have a current that can be delivered if you don't have both terminals on. In the case what we're showing here is it's just basically use a dispersive. Sometimes the dispersive pad, you just stick it on the skin. Other times you use like just a regular agent such as water. But that serves as your dispersive electrode. Now, if your ion was going to be a positive charge, like for instance a common positive ion used in iontophoresis is lidocaine. So lidocaine possesses a positive charge, so if you were going to apply lidocaine, which is a numbing agent, you would have to use the positive lead because, again, like repels like, that would help push it through the skin. So that's the most common and probably most regularly used application of this. There are some other instances with your basic electrical stim, like for instance with high volt, where the positive and negative charge impacts the treatment through kind of a different mechanism, but in particular with ionophoresis, this becomes very important.